Last time we started section 3.4, we were looking at multiplication of whole numbers, and we had just taken a look at the properties that exist for whole number multiplication. We had seen the closure property, the commutative property, associative, the multiplicative, now identity, multiplication property of 0, and the distributive property, and we did an example. Number 3, example 3, actually goes back to those ideas. So JJ claims that the following is true by the distributive law, where A and B are whole numbers. 3 times the quantity A times B is 3 times A times 3 times B. How would you help him out? Okay, so with any claim kind of problems from someone, we want to examine whether or not we think they're correct or incorrect, and then start from there. So, is he correct or is he incorrect?
Oh, he's incorrect.
Ooh.
I thought he was correct until, but isn't it supposed to be a plus?
Okay, so somebody who says that he's incorrect. It's one person. All right, so we'll go with Candace. Candace, what did you see about this that made you think he was incorrect?
The second part, 3 times A should be 3 times A plus 3 times.
Okay, so if this property were holding, there would have been an addition sign here, I think is what you're saying, maybe? And then we would have had an addition sign in between here, right, like that, right? So is it true if there's no addition sign? Because clearly if you put in the addition sign, it is in fact really the distributive property. Is it true the way he's done it? Hallie? Oh, I thought you were raising your hand. You're no. Okay, Emily, what do you think?
I thought that like if you did the distribution to like the 3A times 3B would be the same thing as the same, the 3 times A and then 3 times B.
Okay, but why? And how could you know for sure?
If you plug numbers into
Great.
it.
So let's try that. So if you aren't quite sure, because some of you are saying yes and some of you are saying no, some of you are noticing there's not addition, but the question should be, does it matter, right? If there isn't addition, you're right, but does it matter? So let's try a couple of numbers. I usually try to avoid zeros and ones when I'm plugging things in because unique things can happen with them. And we're trying to see whether or not this sort of fails royally or whether it seems to fulfill its obligations. So maybe you decide you're going to pick 2 and 4, let's say, okay? So let's try that. If I do it on the left, 2 times 4 is 8, and 8 times 3 is 24. So on the left, I get 24. Over here, if I do 3 times 2, I get 6, and 3 times 4, I get 12. What is 6 times 12? Not addition, multiplication, yeah. Multiplication, it's okay. 72 is correct. It's not the same. How much different is it than 24? Can you tell? 3 times, right? If I take 24 times 3, I have 72. So JJ's premise is not right because we showed an example where it's a failing, right? It's a counterexample. It's not right. So we could start talking about what Candace mentioned and what I think Jenna was going for too, in the fact that we don't see the addition sign, right? So therefore, it's not the distributive law. We can also talk about what law it is. So let me actually erase this for the moment. Can you tell what property is actually at play here? It's because it's not the distributive law. It is. Law, property, whatever. But it's not the distributive law or property because multiplication, or let me say it that way, that is multiplication over either addition or subtraction, actually. This one's all multiplication. So we actually have the associative property. So if we wanted to rewrite 3 times AB, the best case scenario, like the most that I could do, is that I could regroup it so that the 3 times A is together if you wish, and then times B afterwards. And you should be able to see why we had that extra 3 showing up is because we included an extra 3 when we tried to do something that looked like the distributive property and ended up with that 72 earlier. This is actually a really common arithmetic error that I see happen all the time in my algebra courses. So definitely something that students confuse which and where they can use what's called a distributive property.
And the bottom line, it would make it right.
Say again.
The bottom,
Over here, you mean?
yes,
Okay.
is what he should have done.
Yeah, if he wants to do some sort of a regrouping where the 3 is grouped with something, the best he can do is this.
Okay.
Right? That's the most he can sort of adjust or change. Yeah. Okay.
What's the word on the second line before over?
Multiply. Sorry, it's M-U-L-T. Multiply. Sorry, I abbreviate multiply, and I abbreviate several words a lot. It's multiply. It's because it's so small. That's a little bit better. It's kind of still almost looks like malt. Have you ever had a malt? It's kind of like a shake, but they've got an extra flavoring added in. So, all right. We're going to shift gears slightly. This is still related to the idea of multiplication, but we're going to take a look at exponents in this section. So by definition first, an exponent a to the n is a times a times a, all of this. This is n times. For a rational number a is called the base, and the exponent, the natural number is called the exponent. That's that n. So what I like to do when I teach this is I like to show you what the rules are, but then I like to show you why the rules are what they are for a couple of reasons. Number one, if you were into an environment where you couldn't remember what the rule was, like you were taking an OSAT or an OGET or something like that, and you can't remember if I'm supposed to add the exponents or I'm supposed to multiply the exponents. If I teach you how to think about them, you might be able to figure out which one you're supposed to do and do it properly. Also, if you have a child in your class ask, but why, Miss Brown, right? Why do we add them instead of multiplying? Even if you can't remember on the spot, you know you've learned it before and you can go back and you can remember how to do that because there is a reason why that you've seen before. Okay? So we're going to take a look first at the four basic properties in this section. If you've had proportional and statistical reasoning, we do these same properties, but we actually go a little bit further into this. The first one talks about when we have the same base repeated with either the same or the different exponents, and what we do is we end up adding the bases together. So a to the m times a to the n is a to the m plus n. So it looks like that we end up with the multiplication of bases becoming the addition of the exponents. So if I take that and I extend that idea to division of the bases, it will end up being what with the exponents? Subtraction, right. So we will have a to the m minus n. So we subtract the top exponent minus the bottom. Number 3, which looks a little bit like number 1, only has one base, right? Number 1 had 2 bases with exponents. This is only the one over 1 base, and so it's like got an exponent raised to the exponent. And when that happens, we multiply the exponents together. Okay, so we have m times n. And number 4 is basically a distribution property. It's distribution of exponents over multiplication, specifically multiplication. So, whoops, wrong one, down here. We end up with a to the m, b to the m. Even on some papers I'm grading from an advanced math class right now, you can't do this over addition. It doesn't distribute. This is a no-go. You cannot distribute over addition. The distribution only occurs over multiplication. And I've had 3 students in that class make this mistake at least. So it's definitely, again, one of those common mistakes, even as you continue on the line. So I want to talk to you about the why. Why in the world do they become addition or subtraction or multiplication or distribution? And so we're going to do this in all the cases actually with examples. So this is supposed to be addition, right? A to the m plus n. So we're going to do this by example and show why it has to work. And the example I'm going to choose is a cubed times a squared. So a cubed means what? A times A times A. That's really what it means, you bet. What does A squared mean? A times A. And how many A's do you have? In total, 5. This is A to the 5th. And how do I get from 3 and 2 to 5? I add. So if you were in an environment where you couldn't remember, do I add or do I multiply, you could change the problem. We learned problem-solving strategies back in Chapter 1. You could change the problem to a very simple example, right, with small exponents, and you can actually see what happens and decide, did I add or did I multiply, and then you'll know. So the next one is supposed to be subtraction of exponents. So we're going to do an example where we have A to the 4th over A to the 1st. So A to the 4th is 4 A's. And when you divide a whole bunch of A's by 1A, what's going to end up happening to your A's? Yeah, one of them is going to cancel out because it's multiplication, right? You can't just cancel numbers in general, but because they're multiplied on top and it's divided on bottom, you can. That leaves me with how many A's? 3. And how do I get from 4 and 1 to 3? Subtract. Exactly. Okay, so the next one, which is often confused with the first one, it is multiplication of exponents. So let's do an example. We're going to do A cubed squared. So A cubed means I have A times A times A, like this. And then squaring means I do something, whatever's in parentheses, twice. So it looks like this. And how many A's do I have? 6. So again, how do I get from 3 and 2 to 6? Multiplication. The last one is the distributive property. And we're going to do A times B to the 3rd. So when I have something multiplied 3 times by itself, right, A to the power 3, that means 3 times by itself, we can write it like this. And we have a whole collection of properties that allow me to rearrange this. Everything here is multiplied. So one of my properties of multiplication is that I can associate things in a different order. Right? I can change the parentheses. Another one is I can switch the order of values, right? And so if I switch the order enough, and if I readjust my parentheses enough, I will end up getting the A's together and then the B's together at the end, like so, which gives me the A cubed, B cubed, showing how it distributed over. And that's happening because of the commutative and associative properties of multiplication. Now, I don't show you that so that you show me how to write out all the A's every time I write A to the 5th. That is not our goal. Our goal is to use the properties. That's why we've got them. I'm just showing you the why behind it so that if you need to develop it because you've forgotten in some environment, or if a child asks you at some point in the future, you've had experience in seeing that. So we are going to actually use those properties now on a couple of examples. The first one is A to the 10th, I'm sorry, not A, it's 5. 5 to the 10th times 5 squared times 5 to the 4th. Now you might notice, hopefully you did, along the way with the 3 properties, the first 3 especially, is that the bases have to be the same to do this. And these are all 5s as bases. So there's no combining exponents if the bases are different. But these bases are in fact all the same, they're 5s. So what do you suppose I can do with all those exponents? I can add them, and I don't necessarily need to write this step, but I just want you to look back to be able to know where they came from in case that it is a confusing thing. I am adding them. So this is A to the, I'm sorry, still 5. 5 to the what power? 16. So if you were to jump straight from here to here, it would be totally fine. But we're doing this intermediate step of addition in our head, so. Okay, so B is different. What is the problem with B? Different bases. In fact, none of them match. So there are 2 different ways to do the problem that are both equally good. So let me show you one of them, and then I'll show you the other. The first one is to take the 6 because it's not in its simplest form and to break it down. And you might notice that the 6 is actually 2 times 3, which is the other two bases, right? So I have 2 times 3 to the 4th is what I really have here. So this is 2 to the 4th times 3 to the 4th, like that. And then I have 2 cubed and 3 cubed. Now I have things that do match in the bases, right? 2 to the 4th and 2 to the 3rd would be 2 to the 7th. And then 3 to the 4th and 3 to the 3rd would be 3 to the 7th. So this is one version of an answer that would be perfectly reasonable here. There's another version of an answer though too. But are we okay with this one so far? So I took the 6 because it wasn't broken down and 3 and 2 were, and I broke it down into 3 and 2. So the alternate option to doing that is instead of breaking 6 down, because the 2 and the 3 have the same exponent, we could undistribute the exponent so that it looks like this. So this is 6 to the 4th times 2 times 3 to the 3rd. So I'm using property number 4, but backwards. Normally property number 4, we'd start with what we just ended with here, 2 times 3 to the 3rd, and we would distribute the 3 out, and we'd end up with 2 cubed, 3 cubed. We can go either way with a property, in either direction. And the reason that this is an acceptable or a nice option is because 2 times 3 is 6. So I have 6 to the 4th times 6 to the 3rd, which is 6 to the 7th. And while I recognize that these answers don't look the same, can you see how they are the same? Yeah? And neither one's really better than the other. They're both fine. I mean, you could argue that the first one's better because it's got primed bases. You could argue that the second one's better because it consolidates it all into one single base. Either way's fine. It doesn't matter. Emily?
So if we get a question like this, would you want us to, would it matter how we solved it?
Not at all.
Okay.
Yeah. So if I were doing this on a test or on an answer key for the grader or something like that, it would show both solutions as answers.
Okay.
Yep. Okay, any questions on that? Okay, we're going to jump back in so that the exponent stuff is related to multiplication, which is why it's in this section. We're going to jump back into some multiplication things that are more direct, where we don't have bases and so forth. And what we're going to look at next is we're going to look at the algorithms for multiplication. So the first one is the expanded standard algorithm. So the expanded standard algorithm is much like the expanded algorithms that we saw for addition and subtraction. It takes the numbers and it breaks them down by their place value. So 48 becomes 40 plus 8 and 32 becomes 30 plus 2. And it writes those factors like this before you multiply. So we end up still doing all the multiplication the same way. It's just more clear the place value that I'm actually working with when I do it. So 8 times 2 is 16, right? And then I have 2 times 40, which is 80. So I actually have like 80 plus 16 here. I'll have to fix that in a little bit. On the next one, I need to do 30 times 8. In fact, let me write it down. This is fine. What's 30 times 8? 240. And then I'd need 30 times 40. What is it? 1,200. I just couldn't hear you very clearly. Yeah. So you have these 4 different pieces. You can add them together in whatever order, right? Because addition is commutative as well. It doesn't make any difference. You can add them like in a vertical pattern. You can add them left to right, whatever you'd like. So a lot of people like to reorganize it so that it goes maybe from biggest to littlest, right? So 1,200, 240, 80, and 16. You don't have to do it that way, but that's kind of nice. So when I'm adding, then I've got the 6 over here. 8, 9, 10, 11, 12, 13. So I have 13 here. Carry my 1. That's a 5, and then I have a 1. So I have 1536. So you're breaking it apart in these 4 pieces that get multiplied. Partial products is very, very similar to this, but it puts things into a grid perspective instead of into sort of an extended multiplication strategy. So it looks like this. We start by drawing a rectangle. And however many place values we have, we need columns for it. So like I have 48, so that's a 40 and an 8. So my columns get drawn in to have 2 columns because I have a 40 and an 8. And then I have 32, so I have a 30 and a 2. If I had a 3-digit number, I'd need 3 columns or 3 rows because I'd have to have one for each place value. And inside of each of these grid boxes, you're doing a multiplication problem. So the first grid, again, you can work from wherever you want, but the first corner, the top left-hand corner, is 40 times 30. That's 1,200. If you move across to the right, you have 8 times 30, which is the 240 we got before. On the bottom left, I have 80. And on the bottom right, I have 16. And then I won't write it out again, but you'd add those all together in a vertical fashion, in a horizontal fashion, your choice. The sum would be 1536. So when my daughter, who's a senior in high school, who's really good at math, she wants to be a math teacher, middle school math teacher, and theater teacher. It's an interesting combination. But when she was first learning to multiply in 2nd grade, she could not for the life of her do the standard algorithm for multiplication. And she was one of the kids that got things quickly, and she couldn't get it. She was being very unsuccessful. And I actually thought, partial products, she's going to get this one. This is my favorite one. Without question, this is my favorite. And it really didn't work very well. But the next one, which is lattice multiplication, was the key. So for quite a while, until she could figure out the standard algorithm, because it's faster, right? She would use the lattice multiplication method. Okay, so you draw a grid box just like the other one, and it's, again, a 2 by 2 because we have 2 2-digit numbers. So however many digits your numbers are, you need them. But you don't write the numbers in their place value. Like you don't write down 40 and 8 for 48. You just write the 4 and the 8. So you put a 4 here and an 8 here. And you put your 3 here and your 2 here. So far, so good? And we saw lattice addition before. And when we did lattice addition, remember we made the boxes split in half? We do that again here. We split our boxes. Instead of adding inside the boxes like we did before, we're going to multiply inside the boxes. Because I'm working with single digits, anytime I multiply single digits together, I always get a double digit. That's the biggest I get, right? Think about it. Your biggest 2-digit multiplication is 9 times 9 and get 81. Still a 2-digit number. Okay, so this works in terms of splitting it. So when I have 4 times 3, I get 12. I put the 1 on the top corner and the 2 on the bottom corner. I do 8 times 3 and I get 24. I put the 2 in the top and the 4 in the bottom. 4 times 2 is 8. Single digit would go in the bottom corner. So that's an 8 down here. And then 8 times 2 is 16. So I do 1 in the top corner, 6 in the bottom corner. So one of the really nice things that happens in both of these methods, actually all 3 of them that we've done so far, the expanded one, the partial products, and this one, is it separates the steps where you multiply and the steps where you add. Did you notice that? Because our standard algorithm mixes those notations together. I don't even have it written down. I'll do it here in just a second so you can see what I mean. But it mixes the notations, and that can make things really confusing for kids. So I've done the multiplication step here, and what I'm going to do is I'm going to just extend my lines over here, okay? So much like with the lattice addition, I have to start in the bottom right-hand corner. That would be a 6. And then I'm adding along the diagonal. So I have 4 plus 1 plus 8. That's 13. So I do the 3 here, and I carry my 1. So I have 1 plus 2 plus 2. That's my 5. And then my top diagonal is a 1. So the answer down here, you can see, is 1536. So I'm isolating the multiplication and the addition steps. So let me show you a couple of things about our standard algorithm that you are still clinging to, even now as I'm showing you other options, because it's very familiar. and about why it can be really confusing. I'll use the same 48 times 32. I guess I don't have a slide for this, probably because I knew you would know how to do it, but I want to show you why this is confusing. First, 2 times 8 is 16, and we're all good with that, and so we write the 6 down and we carry a 1, right? So that feels a little bit like what we do with the regrouping with addition. That part feels the same. But then I have to do 2 times 4, which is 8, and then in the middle of my multiplying, I add the 1 on top. Right? Switch operations, just like that. I'm switched. And so now I've got a 9. That can be confusing. I just switched operations on you, especially when kids isolate what they learn, and you do it too. As you learn one thing, we don't teach you like 6 new things at once. You do one thing until you get it, and then you do another thing, right? Well, now we're incorporating 2 at once. Then this mysterious 0 just shows up out of the middle of nowhere. It's like magic. Somebody says write a 0, and they write a 0. They usually don't know why. There is a reason why. The reason why is because I'm about to multiply by the 3, and the 3 is not really 3, it's 30. That's where the 0 is coming from. But it looks a little bit hocus-pocusy. Just shows up. Then I multiply 3 times 8, which is 24. And then if I'm not careful and I don't remember to sort of erase my 1 here, right, I might accidentally do something with the 1 that wasn't intended to do in this part of the problem at all. And now I have a 2 because the number is 24. 3 times 4 is 12, and once again in the middle of my multiplying I need to add, so I get 14. And then when it's all said and done, I have to add again. Okay, so do you get how this can be a difficult task for a child? It's a lot of things going on all at the same time. That doesn't mean that it's not the most efficient way to do it, the quickest and so forth. It just means that it might take more work than what you thought when you were explaining it. All right, we've got a couple of things then that we're going to look at for mental math and then computational estimation, and we'll be done. So remember, we've talked about mental math before. Mental math means it's something you should be able to do in your head, but you have to do it on paper so that I can see what you're thinking. Make sense? So when we're looking at mental math, sometimes with mental math, it's easy to do front-end multiplying. So what front-end multiplying means we do is we're not estimating again. We're just doing it mentally. Is that we're doing it 1 digit at a time. So I'm taking the 5 times the 40. So I'm breaking it down to say 40 times 5. And I get 200. And then I take my 6 times my 5. And I get 30. And then I can add them together. So that I'm not doing the single digit first, which is what we normally do. I'm doing the larger digit first instead. So my addition actually ends up having lots of zeros usually on the end. When I do it times the 40 part of it, I end up with some zeros on the end, so the addition actually works out really clean later. So front-end multiplying means that I break it down so that I multiply by the first digit first. Compatible numbers, I've mentioned before. We've done it with addition anyway. Sometimes there are numbers that are really nice to add together, and sometimes there are numbers that are really nice to multiply together. Can you tell me 2 digits here that are like really friendly for multiplication purposes? 5 times 5 actually isn't, and the reason it isn't is because it creates a 2-digit number where each digit is not 0.
8 times 5.
8 times 5 is not bad. So this one, by like contrast, creates a 2-digit number, but one of the digits is 0. So anytime I have a 2-digit number where one of the digits is 0, it acts a lot like a 1-digit number. That's why it's compatible, is because I end up getting a 0 somewhere in it. There's another pair. 4 times 5 or 2 times 5. So you can pick your favorite. So I heard you guys say 4 times 5, so I'll do that one. 4 times 5 would be 20. So now what I've broken this down into is these 3 numbers being multiplied. So it doesn't really matter which order you do them in again. If I do these 2, it's kind of nice. 20 times 2 is 40, and then I can take my 40 times my 40 to give me close. 1600. Yeah. 16 and then 2 zeros. So compatible numbers for multiplication actually means I want to get things that are like 10 or 100 or 20 or 40. I'm looking for those kinds of values to show up. I also have a strategy here called thinking money. And thinking money kind of creeps in sometimes. But in particular, what happens is it works nicely when you're multiplying by values that we have coins for. It's all about coins. So this one, 46 times 5, is actually really nice to do thinking money because we have a coin with a value of 5. Not 46, but 5, right? A coin has a value of 5. Nickel. So this is the equivalent of saying I have 46 nickels. Okay? A 5 is a nickel. But it'd be a lot easier if I didn't have nickels and instead had dimes. So if I have 46 nickels and I trade you for dimes, how many dimes would you give me back if you're not cheating me? How many? 23 dimes. A dime is worth 2 nickels. So I take my 46 and I divide by 2. So why? Because 23 times 10 is easier than 46 times 5. Right? A dime is worth 10, whereas a nickel is worth 5. What's 23 times 10? 230. You didn't have to write anything down. I mean, like computationally speaking, you didn't have to use calculator because it's times 10. And you just tack a 0 on the end. Does that make sense? So it's really useful when you're working with times 5s, right, nickels, or times quarters. 25 is a quarter, right? So this is saying I have 44 quarters. Now, I do not want to turn my quarters into nickels. I don't want to make things smaller. I'd like to make them bigger. What's a really nice ratio you know about quarters that you can make into some sort of a bigger denomination? Into a dollar, right. So if I had dollars, how many dollars is 44 quarters? It's 11. Okay?
That would take me like 5 minutes to figure out.
So if you want to remember so that a quarter, 4 quarters equals $1. So what I'm doing is I'm dividing by 4. That's where the 11 came from. Okay? That's why it worked. Over here, I divided by 2. Actually, let me move this part. Because 2 nickels equals 1 dime, so I divided by 2. That's why I used 2. Yeah, so I get $11, but in the context of what we're working with, if a quarter is 25, what's a dollar? 100. And multiplying by 100 is easy. It just means I tack 2 zeros onto the end of the number. So this is 1100. Okay? Mental math times 25. All right, we're going to do one example with some computational estimation. So estimation, again, means we're not getting the exact answer. We're getting an approximation. So this is actually computational estimation that is employing that front-end strategy. So front-end was over here. So the front-end multiplying means that I use just the first 2. Well, what it means is I multiply each of the digits out individually times the 5 in this case. So what I'm going to do when I do estimation is I'm just going to do the first 2. The problem with thinking like this, the front-end multiplication, is you reach that capacity of 3 steps in your head really quickly, right? I multiplied by 40, I multiplied by 6, and then I added them together. That's 3 steps. If I were to try to do this problem out, I'd have to, like in full, like for the exact value, I'd have to multiply by 300, I'd have to multiply by 80, I'd have to multiply by 6, and then I'd have to add them, and it's a 4-step process. So that's why this one is showing up underneath the computational estimation section instead of the mental math section, because we're trying to do it still mentally, but by abbreviating the steps. So it looks like this. We take the 3 and the 300 and we multiply it by 4. And what do we get? 1,200. Good. And we take the 80. Grace, you have a question?
300, we're going down.
We're looking at just the digit itself in the hundreds place.
Oh, not
so the 3, no, we're not rounding anything. We're just looking at the digits that's there. So the 3 because it's in the hundreds place. And then we're going to look at the 8 because it's in the tens place.
Okay.
So 8 times 4 is 320. And then if I add 1,200 and 320 together, I get 1,520. And this isn't exact, right? It is an approximation for this because I'm doing the estimation section. Emily.
Since it's a front end
Right, because front-end estimation as opposed to front-end multiplying means I'm still gonna stick with the first 2 digits because I'm doing a 3-step process.
Okay.
I'm only doing 3 steps, so I only multiply by the first 2 digits. It's not really even like the hundreds digit and the tens digit. If this had 5 digits, we'd multiply by the 10,000s digit and the thousands digit, and then you'd add these values together. That's all you'd do. So it's just the first 2 digits, whatever they are. All right, that's it for today. We're going to take a look at the group work next, and this will be due on Friday.